This video is for those of you who are taking the SAT chemistry subject test. For each of the following questions, I recommend that you pause the video and work on the problems yourself. When you want to see the solution, just play the video and watch it. So let's begin with this problem. So questions 1 to 5 refer to the following. So let's look at number 1. Which of the above properties explains why water has a high boiling point? Is it A, ionic bonding, B, polar covalent bonding, C, hydrogen bonding, D, nonpolar covalent bonding, or E, metallic bonding? What would you say? Why does water have a high boiling point? The reason why water has a high boiling point is due to a property known as hydrogen bonding. Hydrogen bonds is found whenever hydrogen is attached to one of these three elements: oxygen, nitrogen, or fluorine. But it's not within a single molecule, rather it's between two separate molecules. So this here is an H bond or hydrogen bond. The hydrogen atom of one water molecule has a partial positive charge. The oxygen atom of the other water molecule has a partial negative charge. And so opposite charges attract, and that is the H bond. It's a special type of dipole-dipole interaction. So for answer choice for number 1, the answer is A. I mean, not A. I take that back. It's C, hydrogen bonding. Now let's move on to the next statement, number 2. The reason why some solids can conduct electricity is due to which of the 5 types of bonding listed above. So why do some solids conduct electricity? What type of solids conduct electricity? Metals conduct electricity. Metals such as zinc, copper, silver. These metals are highly conductive to electricity. So the answer is due to metallic bonding. So number 2 is E. What about number 3? Which type of bonding allows atoms of chlorine to bond to each other in Cl2? So what type of bonding is described here? Would you say it's ionic bonding, polar covalent bonding, nonpolar covalent bonding? In order for it to be ionic bonding, you need ions. Typically, it's composed of metals and nonmetals. In order for it to be polar covalent bonding, typically it's between two nonmetals, but they tend to be different nonmetals. Because we have 2 of the same type of nonmetal, 2 of the same atoms, it has to be nonpolar covalent bonding, because the electrons are equally shared between the 2 chlorine atoms. The 2 chlorine atoms have the exact same electronegativity values. Now, what about number 4? So which of the following types of bonding allows an aqueous solution of sodium bromide to conduct electricity? Now, sodium bromide is composed of a metal and a nonmetal. Whenever you have a metal paired up with a nonmetal, they form an ionic bond. And whenever you dissolve an ionic compound in water, it will conduct electricity. This is due to the presence of free-flowing ions in solution. So for number 4, the correct answer will be A, ionic bonding. It best explains why sodium bromide conducts electricity when dissolved in water or in an aqueous solution. Now, what about number 5? This type of bonding is found in carbon monoxide. Carbon monoxide is CO. If you draw the Lewis structure, it looks like this. There's a triple bond between the carbon and the oxygen. Now, both carbon and oxygen are nonmetals. And whenever you have 2 nonmetals sharing electrons, it's going to form a covalent bond. But because the elements are different, it's not going to be nonpolar covalent, but it's going to be polar covalent bonding. So the correct answer for this one is answer choice B. Now, one thing I do want to mention is that carbon has an electronegativity value of about 2.5 and oxygen is about 3.5. So the electronegativity difference is about 1.0 according to most textbooks. Now, if the EN difference or electronegativity difference, if it's 0.5 or more, the bond is considered to be a polar covalent bond. If it's 0.4 or less, it's a non-polar covalent bond. So sometimes you may have a bond with two different elements, but it could still be a non-polar covalent bond if the if the electronegativity difference is less than 0.5. So for instance, the carbon-hydrogen bond. Carbon has an EN value of 2.5, and for hydrogen, the electronegativity value is 2.1. So the electronegativity difference between the two elements is 0.4. So the CH bond is not considered to be a polar covalent bond. In fact, it's considered to be a nonpolar covalent bond. So if the elements are different, it could be polar covalent bonding or nonpolar covalent bonding. You need to look at the electronegativity values. Now let's move on to our next set of questions. Number 6. This property is the energy required to remove an electron from a gaseous atom. So would you say that is electronegativity, ionization energy, electron affinity, atomic radius, or metallic character? Now, this is basically a definition type problem, and this is just something you have to know. The energy required to remove an electron from a gaseous atom is basically ionization energy. Because once you're removing an electron from a gaseous atom, you're creating an ion. So basically, it's the energy to create an ion, or ionization energy. You can think of it that way. Now, number 7, this represents the energy absorbed or released when an electron is added to a gaseous atom, as opposed to removed from a gaseous atom. So if you're adding electrons, this is associated with electron affinity. Now what about number 8? The ability of an atom to attract an electron to itself. So this describes electronegativity. On the periodic table, electronegativity increases as you go up and to the right across the table. Fluorine is the most electronegative element on the periodic table. It has a strong desire for electrons. And so fluorine is the most reactive halogen out of all the chemical elements that we know of. Now, I'm going to write En for electronegativity. Ionization energy follows a similar trend. Ionization energy increases as you go up and to the right across the periodic table. So helium has one of the highest first ionization energies. Now what about number 9? This describes the size of an atom. This is going to be atomic radius. A large atom is going to have a large atomic radius. A small atom will have a smaller atomic radius. So atomic radius is basically proportional to the size of an atom. Atomic radius increases as you go to the left and down across the periodic table. So basically it increases towards francium. Now metallic character basically describes the metallic character of an element. It increases in the same pattern as atomic radius, to the left and down across the periodic table. So for instance, francium has a greater metallic character than sodium. So let me give you a visual illustration. Let's say sodium is located at that position on the periodic table. Francium would be here. Aluminum will be somewhere in the middle. Then you have silicon, chlorine, fluorine, and helium. So these are just some elements in the periodic table. Now, notice that francium is lower than sodium. So francium will have a greater metallic character than sodium. The metals tend to be on the left side of the table. The nonmetals tend to be on the right side. So as you go from right to left across the periodic table, the metallic character increases. You're traveling from the nonmetal section to the metalloids to the metals. So sodium has more metallic character than silicon. Metals, they like to give away electrons. Nonmetals, they like to take electrons. And so metallic character can help you to determine which elements behave more like metals and which ones do not. Now, for the next 5 problems, what you need to do is determine if the first statement is true or false. And you need to do the same thing for the second statement. Now, once you do that, you need to determine if the second statement supports the first statement. Like, you need to determine if the second statement is a correct explanation of the first statement. If that's the case, then you need to select the option CE. If it doesn't support it, on a test, do not select the option. What I'm going to do is put an X on CE. So let's begin. Number 10. When a liquid changes into a solid, the process is exothermic. So let's focus on that statement. Is that a true statement or is it a false statement? So let's say if we use water for an example. When liquid water turns into basically solid water or ice, is heat absorbed or is heat removed? In order for you to freeze water into ice, you need to remove heat. And the process of removing heat is exothermic. Whenever a process releases energy or heat is removed from it, that's an exothermic process. So number 10 is a true statement. Going from a liquid to a solid is an exothermic process. Now, let's see if statement 2 is true or false. Solids have less potential energy than liquids. Is that true or is that false? What would you say? Statement 2 is true, but let's understand why. Let's revisit the heating curve of water. On the y-axis, we have temperature, and on the x-axis, we have the time. And we're adding a constant flow of heat into water. So first, we're going to start with ice, the solid phase of water. Now, as you add heat to ice, the temperature will increase. Once it gets to 0, the temperature stops increasing. All of the ice molecules will be melted into liquid water. And once that happens, the temperature will increase again. Now, once the temperature reaches 100, the liquid water molecules will begin to change to steam. So they're going to go from liquid to gas. Now, once all of the liquid molecules have been converted to gas molecules, the temperature will increase again. So here we have a solid, liquid, and a gas. Now, what you need to understand is that whenever the temperature increases, the kinetic energy of the molecules is increasing. But what about when the temperature is not increasing? Let's say when a solid changes to a liquid, or when a liquid changes to a gas. Because during that part of the heating curve, the kinetic energy is not increasing. So what's increasing? It turns out that the potential energy is increasing during the phase change. So as we add heat, when the solid becomes a liquid, the potential energy is increasing. So that means that liquids have a greater potential energy than solids. And so the reverse statement means that solids have less potential energy than liquids. So that's why statement 2 is true. Now, does statement 2 support statement 1? When a liquid changes into a solid, Is the process exothermic because solids have less potential energy than liquids? So now, looking at statement 1, we're going back from a liquid to a solid. Because the potential energy is decreasing, energy has to be released. In order to increase the potential energy, energy has to be absorbed. So in this heating curve, going from a solid to a liquid, we were putting energy in. So that's an endothermic process. But for statement 1, the reverse is true. We're going from a liquid to a solid. So the potential energy has to be decreasing. And because solids have less potential energy than liquids, energy will be released, and so the process is exothermic. So statement 2 supports statement 1. On a test, you need to select this option. But for future problems, I'm just going to put a check mark next to the word because, meaning that number 2 supports number 1, just to keep things simple. Now, what about number 11? What do you have to say about that? Lithium metal is a strong reducing agent. Is that true or false? Lithium is an alkaline metal, and metals like to give away electrons, which is a characteristic of reducing agents. And alkali metals are the most reactive metals on the periodic table. So lithium is a strong reducing agent. It really wants to give away its electrons. Now, what about statement 2? Is it true or is it false? An atom of lithium readily gives up a valence electron. Well, we just answered that question. We said that strong reducing agents like to give up electrons. So this is a true statement. And statement 2 supports statement 1. Lithium metal is a strong reducing agent because an atom of lithium readily gives up a valence electron. So let's put a check mark next to the word because. Number 12. Carbon-12 and carbon-13 are isotopes of each other. Is that true or false? This is a true statement. The numbers 12 and 13 are the mass numbers of the isotopes. Isotopes are composed of the same element, but they have different mass numbers. Now, what about statement 2? Do isotopes have the same atomic number? Is that true or false? This is a true statement. Carbon-12 has a mass of 12. Carbon-13 has a mass of 13. But they are still carbon atoms, and all carbon atoms have an atomic number of 6. So these two isotopes have the same atomic number. Now, does statement 2 support statement 1? Carbon-12 and carbon-13, are they isotopes of each other because isotopes have the same atomic number? No. Because let's say if we have another carbon-12 atom, these are not isotopes of each other, yet they have the same atomic number. Now, the reason why these two are isotopes of each other is because they're composed of the same element, but they have different mass numbers, and thus they have different number of neutrons. The number of neutrons is the difference between the mass number and the atomic number. So carbon-12 has 6 neutrons, carbon-13 has 7 neutrons. 13 minus 6 is 7. And so that's how isotopes differ from each other. They have different mass numbers and different number of neutrons. Now, there's something else that you need to understand about isotopes. Their chemical reactivity is the same, but their nuclear reactivity is different. Carbon-12 and carbon-13, they behave the exact same way in a chemical reaction. The arrangement of their electrons are the same. Now, in a nuclear reaction, it's different. The nucleus of carbon-13 is different than the nucleus of carbon-12 because the number of neutrons are different. So in terms of a nuclear reaction, carbon-12 and carbon-13, they behave differently. Now, let's move on to the next one. Number 13. In order for a liquid to change into a gas, covalent bonds must be broken. Is that true or is that false? So let's use water as an example. In liquid water, the molecules are very close to each other. But when water turns into a gas, or basically steam, the molecules are separated from each other. But it's still water though, it's still H2O. Now, you need to know the difference between a hydrogen bond and a covalent bond. So the bond highlighted in blue, that is an H bond or a hydrogen bond. The bond highlighted in red, that is inside a molecule, that is a covalent bond. So make sure you understand that covalent bonds are within a single molecule, but hydrogen bonds are between two separate molecules. Now, when you add heat, when you change liquid water into steam, you're not really separating the hydrogen atoms from the oxygen atoms, because steam is still H2O, it's still water. Instead, what you're breaking is the hydrogen bond, because you're separating water molecules from each other. And so whenever you turn a liquid into a gas, you're breaking the intermolecular bonds between molecules. You're not breaking the covalent bonds. So number 13 is a false statement. Now, I want you to understand something. If you were to break the covalent bonds, this would be like electrolysis, where water will be broken down into hydrogen and oxygen gas. In this case, to break the chemical bonds or the covalent bonds, you're basically changing the compound itself. You're changing water into a completely different substance, like hydrogen gas or oxygen gas. In that case, that's when the covalent bonds will be broken. But if you're going to boil a liquid into a gas, you're not breaking a covalent bond. The chemical identity of the substance is not changing. So it's not a chemical reaction, it's a physical reaction. One thing I forgot to do is put an X for number 12. Statement 2 does not support statement 1. So I want to make sure I write that there. Now, going back to number 13, statement 2. Heat is absorbed when a liquid changes to a gas. Is that true or false? So let's say if we have liquid water. In order to convert it to gaseous steam, do we need to add heat or should heat be removed? You need to put the water on a stove. You need to boil it. So you have to add heat. Which means that the second statement is a true statement. Heat is indeed absorbed when a liquid changes to a gas. Now, does statement 2 support statement 1? In order for a liquid to change into a gas, covalent bonds must be broken because heat is absorbed when a liquid changes to a gas. Statement 2 supports the first portion of statement 1. It does not support the second portion of statement 1. So because it does not support this portion of the statement, we have to put false, meaning we will not select the CE option for that problem. Now, what about number 14? Sodium metal has a low electronegativity value. Is that true or is that false? Now, recall the trend for electronegativity. It increases as you go up and to the right. So it increases towards fluorine. What you need to know is that nonmetals like fluorine have high electronegativity values because they have a strong desire to attract electrons to themselves. Metals like sodium have a low electronegativity value because they don't want to take electrons, they want to give it away. Lithium and sodium, they're in the same category. They are strong reducing agents. They're alkaline metals. They like to give up electrons. And so statement 1 is true, but statement 2 is false. Sodium does not have a strong attraction for electrons. It wants to give away its one valence electron. So because statement 2 is false, it cannot support statement 1. Sodium metal has a low electronegativity value, not because sodium has a strong attraction for electrons, but because sodium wants to give away electrons. And so we need to put an X for that option. Number 15. What is the oxidation state of manganese in potassium permanganate? And we're given the formula KMnO4. How can we determine the oxidation state of an element in a compound? Now notice that this compound is not a polyatomic ion with a net charge. The total charge or the net charge of a compound is 0. So what you want to do is write an equation. You want to list out all of the elements in the equation and set it equal to the net charge, which is 0. So we have 1 potassium atom, 1 manganese atom, and 4 oxygen atoms, and it equals a total charge of 0. Now potassium is an alkali metal with 1 valence electron, but in this compound it's an ion. It's an ion with a +1 charge. So whenever you see potassium in an ionic compound, the oxidation state will be +1. So we can replace K with 1. Our goal is to calculate the oxidation state of Mn. So let's replace that with X. Now what is the oxidation state of oxygen? Now this is a rule that you need to know. Oxygen typically has an oxidation state of -2 unless it's bonded to fluorine or if it's not in its elemental state, because any element in its natural elemental state as a pure element has an oxidation state of 0. The other things you need to watch out for are compounds that contain peroxides and superoxides. In a peroxide compound, the oxidation state of oxygen is -1. In a superoxide compound, it's -1/2. But these are rare instances which you probably don't have to worry about. Now let's finish the problem. So 4 times -2 is -8. And we can combine these numbers. 1 plus -8 is -7. Our next step is to add 7 to both sides. So we can see that X is equal to +7. So this is the oxidation state of manganese in the compound potassium permanganate, which means that answer choice E is the right answer. Number 16. What is the percent by mass of aluminum in aluminum sulfide? So before we can calculate the mass percent, we need to determine the correct formula of aluminum sulfide. So we have an ionic compound. Aluminum is a metal, sulfur is a nonmetal. Now, aluminum has a charge of 3+. Sulfur, as an ion, has a charge of 2-. And you could use this technique. You could switch the charges with subscripts, and you'll get the formula Al2S3. To balance out the charges, we need 3 aluminum cations. A cation is basically an ion with a positive charge. We need 2 aluminum cations and 3 sulfide ions. An anion is an ion with a negative charge. So notice that the 3 sulfide ions has a total negative charge of 6, and the 2 aluminum cations has a total charge of +6. So based on this 2:3 ratio, the charge is balanced. So that's how you can determine the chemical formula of an ionic compound. So it's Al2S3. Now, in order to determine the mass percent of an element, we need to take the mass of that element and divide it by the mass of the compound. And we're going to multiply it by 100%. So we want to find the mass percent of aluminum. We need to take the formula weight or the atomic weight of the 2 aluminum atoms, and divided by the formula weight of the entire compound, which consists of 2 aluminum particles and 3 sulfur particles. So at this point, we need to use the periodic table. The average atomic mass of aluminum based on the table is 26.98. And the average atomic mass of sulfur is 32.06. So 2 times 26.98, that's going to be 53.96. And then 3 times 32.06, that's 96.18. And let's not forget to multiply everything by 100%. So you should get 35.94% as your final answer. So this is the mass percent of aluminum in aluminum sulfide. Number 17. Which of the following substances is amphoteric? So what is an amphoteric substance? An amphoteric substance is a substance that can behave both as an acid and as a base. So water is a good example of an amphoteric substance. Water can behave as an acid by giving away a proton. If it loses a proton, it turns into hydroxide. Now water can behave as a base by accepting a proton, turning into the hydronium ion. Keep in mind, bronzolari acids are proton donors and bronzolari bases are proton acceptors. So because water can behave as a base by accepting a proton, or it can behave as an acid by releasing a proton, it's an amphoteric substance. So looking at the answer choices below, which ones can we eliminate? Which ones are definitely not acids? Which ones cannot behave as an acid? In order for a substance to be amphoteric, it has to be able to give a proton. So we can eliminate answer choice A, D, and E because they don't have a hydrogen atom. They can't donate a proton. And so they can't behave as a bronzolari acid. Now let's look at answer choice B, hydrofluoric acid. HF can give away a proton, and so it's an acid. But will it accept a proton? HF is not typically known for accepting protons, so therefore it can act as an acid, but not necessarily as a base. So HF is not considered to be amphoteric. Now what about H2PO4-? H2PO4- can act as an acid. It can give away a proton easily, becoming monohydrogen phosphate. H2PO4- or dihydrogen phosphate can also accept a proton, turning into phosphoric acid. So this compound, but that ion or polyatomic ion can behave both as an acid and as a base, which means that it's amphoteric. So C is the right answer. Number 18. What is the coefficient of O2 when the equation shown below is balanced using the lowest whole number terms? So let's begin by balancing this equation. Let's start by analyzing the carbon atoms. Notice that we have 6 carbon atoms on the left side. We only have 1 on the right. So to make the number of carbon atoms equal, we need to put a 6 in front of CO2. Our goal to balance this equation is to make sure that the number of atoms on the left side is the same as the number of atoms on the right side. Now notice that we have 14 hydrogen atoms on the left, only 2 on the right. 14 divided by 2 is 7, so we need to put a 7 in front of H2O. Now the last thing we need to balance is the number of oxygen atoms. So in the 7 water molecules, there's a total of 7 oxygen atoms. In the 6 CO2 molecules, we have 12 oxygen atoms because 6 times 2 is 12. Each CO2 molecule contains 2 oxygen atoms. So now if we add 12 plus 7, that's going to give us 19. So in order to balance this equation, we need to take 19 divided by 2, and we'll get the fraction 19 over 2. So right now the equation is balanced, but it's not balanced using lowest whole number terms. So we need to get rid of this fraction. So what we need to do is we need to multiply all the coefficients by 2. That will get rid of that fraction. So initially we had a 1 here because there was no number, but now it's going to be a 2. Before we had 19 over 2 here. If you multiply that by 2, that's just going to be 19. We had a 6 in front of CO2, but if we double it, it's going to be 12. And we had a 7 here, so that's going to be 14. So now notice that we have 12 carbon atoms on both sides. And we have a total of 28 hydrogen atoms on both sides. 2 times 14 and 14 times 2, they're the same. Now for the number of oxygen atoms, we have 14 in front of the 14 water molecules. 12 times 2 is 24. And 19 times 2 is 38. And 24 plus 14 is 38. So we now have the same number of carbon atoms, hydrogen atoms, and oxygen atoms on both sides. So the equation is now balanced. So we're looking for the coefficient of O2 in the balance equation. So that's the number in front of O2, which is 19. So E is the answer. Number 19. What is the molecular structure of NH3? Nitrogen has 5 valence electrons. Hydrogen has 1. So in the NH3 molecule, we have N plus 3H, or basically 5 plus 3. There's a total of 8 valence electrons. Now hydrogen can only form a single bond. So because we have 3 single bonds, and each single bond carries 2 electrons, so far we have a total of 6 electrons in this molecule. So to get to 8 electrons, we need to put a lone pair. This is the structure of NH3. And you need to know that this particular structure, where the central atom is attached to 3 atoms and has 1 lone pair, that structure corresponds to the trigonopyramidal structure. Therefore, D is the right answer. Number 20. Which of the following is a polar molecule? Is it going to be answer choice A, B, C, D, or E? What would you say? Well, let's analyze each answer choice to find the answer. Now, let's start with answer choice A, CO2, carbon dioxide. Now, in order to answer this question, you need to be able to draw the Lewis structure for each of these molecules. If you need to know how to do that, there's a video that I created that'll help you to master that topic. So if you go to the YouTube search box, type in Lewis Structures Organic Chemistry Tutor, and you should see a video come up that will help you with this. It's basically a 2-hour video, but it'll really help you to master how to draw Lewis structures. Now let's start with carbon dioxide. Carbon has 4 valence electrons. Oxygen has 6. So in CO2, it's going to be 4 plus 2 times 6. So that's 12 plus 4, which is 16. So we have a total of 16 valence electrons in CO2. Now 16 is a multiple of 8. So that tells us that we're not going to have any lone pairs on the central carbon atom. Now, it's important to understand the number of bonds that certain elements like to form. Hydrogen likes to form 1 bond. Beryllium likes to form 2 bonds. Boron likes to form 3. Carbon likes to form 4. And the next one is nitrogen, which likes to form 3 bonds. Oxygen likes to form 2. And halogens like fluorine, typically they like to form 1. Now, these are some general rules. There are exceptions, but knowing this will help you to quickly draw the Lewis structure. So oxygen likes to form 2 bonds. Carbon likes to form 4. In this arrangement, both oxygen atoms have 2 bonds and the carbon atom has 4 bonds. And there's a total of 16 electrons. Keep in mind a double bond represents 4. So we have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. So the geometry for this particular molecule is linear. Now, is the molecule polar or nonpolar? The carbon-oxygen bond is a polar bond. Now, what does it mean for something to be polar? An object that is polarized is neutral overall, but there's separation of charges. One side is going to be positive, the other side is negative. So that is a polarized object. The carbon-oxygen bond is polar because carbon bears the partial positive charge, oxygen bears the partial negative charge. Oxygen is more electronegative than carbon. The En difference is greater than 0.5. So the CO bond is polar. But is the molecule polar? Well, we need to draw something called the dipole moment. And we're going to draw an arrow starting from the positive charge pointing to the negative charge. Notice for these 2 double bonds, the 2 arrows, they go against each other, so they cancel out. So even though CO2 has polar bonds, it's a nonpolar molecule because the net dipole moment is 0. These 2 arrows cancel out. So we can eliminate answer choice A. CO2 is a nonpolar molecule. Now what about BF3, boron trifluoride? Is it polar or nonpolar? So if we count the number of valence electrons, boron has 3 valence electrons, fluorine has 7 and there's 3 of them. 3 times 7 is 21 plus 3 is 24. 24 is a multiple of 8. And when you see this, typically, there's not going to be any lone pairs on the central atom unless hydrogen is involved. Hydrogen is the exception. The Lewis structure for BF3 looks like this. Each fluorine atom will have 3 lone pairs. So this is 2, 4, 6, 8 electrons. This is another 8 electrons, that's 8. So we have a total of 24 electrons. Thus, there's no lone pairs on the boron atom. Now, fluorine is more electronegative than boron. So fluorine will carry the partial negative charge. Boron will carry the partial positive charge. So drawing the dipole moment, it's going to look like this. Now, keep in mind, the boron-fluorine bond is a polar bond. Boron has an electronegativity value of, I believe it's like 2.0, and for fluorine it's 4.0. So this is definitely a polar bond. But is the molecule as a whole polar? Do the arrows cancel out? What would you say? So you need to view these arrows like vectors. The first vector goes up. The second one goes this way, and the third one goes this way. Now the 2 vectors on the bottom, you want to break it down into x and y components. Notice that the x component of the second vector cancels with the x component of the third vector. One is going to the left, the other is going to the right. Now notice that the y components of the 2 vectors on the bottom cancels with the vector on top. So these 3 vectors are arranged in such a way that they completely cancel. So there's no dipole moment for this molecule. The net dipole moment is 0, which means that BF3 is not a polar molecule, but a nonpolar molecule. Now let's move on to answer choice C, CH4, methane. Carbon has 4 valence electrons, hydrogen has 1, so the total number of valence electrons is 8. Now keep in mind, hydrogen likes to form 1 bond. So this is the Lewis structure for methane. The geometry is tetrahedral. And by the way, the geometry for the BF3 molecule is trigonoplanar, just in case you were curious about that. Now what can we say about methane? Is it going to be polar or nonpolar? Earlier, we discussed that the CH bond is a nonpolar bond. Carbon has an electronegativity value of 2.5, and H is about 2.1. So because the electronegativity difference is less than 0.5, the CH bond is not polar. So therefore, the CH4 molecule can't be polar. So this is a nonpolar molecule. So anytime you have a molecule that is a hydrocarbon, meaning that it's completely composed of carbon and hydrogen, it's going to be a nonpolar molecule if there's no other elements attached to it. Now what about SF6, sulfur hexafluoride? Sulfur has 6 valence electrons, fluorine has 7, but there's 6 of them. 6 times 7 is 42, plus 6, that's 48, which is a multiple of 8. So there's not going to be any lone pairs on the central sulfur atom. Sulfur hexafluoride looks like this. It has an octahedral molecular geometry. And it turns out that all of the dipole moments cancel in this molecule. So the net dipole moment is 0. As you can see, the dipole moments between these two, they cancel. Between those two, they cancel. And then the other two, they cancel as well. So by default, we know that the answer has to be SO2. But now looking at CO2 and SO2, they appear to be very similar. But there's one key difference about SO2 that distinguishes it from CO2. Let's begin by drawing the Lewis structure of SO2. Sulfur has 6 valence electrons, and the same is true for oxygen. So 6 plus 12 is 18. 18 is not a multiple of 8. But if you subtract 18 by the highest multiple of 8, just under 18, this will give you 2, which tells us that sulfur has 2 electrons, or 1 lone pair. Now oxygen likes to form 2 bonds. So this is the Lewis structure for sulfur dioxide. So because sulfur have 2 more valence electrons than carbon, it forms a bent molecular structure. And because it's bent, it's no longer linear, it's going to be polar. The dipole moments will not completely cancel out. Oxygen is more electronegative than sulfur. That's why the arrows are pointing towards oxygen. So if we analyze the vectors, we have one going this way, one going that way. Notice that the y components of the vectors do not cancel. They add up. They point in the negative y direction. The x components cancel, but not the y component. So these two vectors, they partially cancel, but not completely. So there is a net dipole moment that points downward along this page. So because there's a net dipole moment, SO2 is a polar molecule. So answer choice E is the right answer. 21. Which of the following substances is the oxidizing agent in the reaction shown below? In order to answer this question, we need to determine which reactant is oxidized and which one is reduced. So we need to calculate the oxidation states of every element. Now the oxidation state of a pure element is 0. So for zinc metal and hydrogen gas, the oxidation state is 0. Now, what is the oxidation state of hydrogen and chloride in HCl? In HCl, hydrogen has a +1 charge, chloride has a -1 charge. So we could put +1 for hydrogen, -1 for chlorine. Now, in zinc chloride, chloride still has a charge of -1. But what's the charge of zinc? Now, there's 2 chloride ions, so zinc has to have a 2+ charge. So the oxidation state of zinc is +2. So zinc goes from an oxidation state of 0 to an oxidation state of 2. Would you say that zinc is oxidized or zinc is reduced? Because the oxidation state of zinc increased, zinc was oxidized. Whenever a substance is oxidized, that means that it loses electrons. The substance that is oxidized is the reducing agent because it causes the other reactant, HCl, to be reduced. Now, it's the hydrogen part of HCl is being reduced. You can see that. Look at the oxidation state. The oxidation state reduces from 1 to 0. So we can say that HCl is reduced, which means that it is the oxidizing agent. So I'm going to rewrite this like this. The oxidation number of hydrogen decreased. Whenever the oxidation number goes down, we could say that the substance is reduced, which means that it's the oxidizing agent. It's the oxidizing agent because it causes the other substance, zinc, to be oxidized. So whenever the oxidation state goes up, the substance is oxidized, and therefore it's the reducing agent, and that substance loses electrons. Now, whenever the oxidation state goes down, the substance is reduced. It's called the oxidizing agent, and that substance gains electrons. In order for the oxidation state to go from 1 to 0, there's a gain of 1 electron for 1 atom of hydrogen. Now, the answer to this question is going to be HCl, because the hydrogen that was reduced is part of the HCl substance. So HCl is the oxidizing agent in the reaction shown below. It's important to understand that active metals that like to give away electrons are reducing agents. Nonmetals that like to acquire electrons tend to be oxidizing agents. And certain metal ions which acquire electrons are oxidizing agents. So make sure you get that. Anything that likes to give away electrons are reducing agents, and substances that like to acquire electrons are oxidizing agents. 22. Hydrosulfuric acid reacts with oxygen gas to produce sulfur dioxide and water. How many moles of oxygen gas is required to completely react with 5.3 moles of hydrosulfuric acid? So what should we do in this problem? The first thing we need to do is write a balanced chemical equation. Hydrosulfuric acid is H2S. Oxygen gas is O2. Sulfur dioxide, SO2. Water is H2O. So if you want to balance the chemical equation like this, you could. You can write out the different elements that you have on the reactant side and on the product side. Right now on the left side we have 2 hydrogen atoms, 1 sulfur atom, 2 oxygen atoms. On the right side we have 2 hydrogen atoms, 1 sulfur, and 3 oxygen atoms. Now it's best to save this for last. Actually, we can go ahead and balance it now. The number of hydrogen atoms are equal to each other. The number of sulfur atoms are equal. The only thing we need to do is balance the number of oxygen atoms. We have a total of 3 oxygen atoms on the right side, 2 on the left. 3 divided by 2 is 3/2. So if we put 3/2 here, it's going to be balanced. However, we don't want any fractions. So we need to multiply everything by 2. So these are the numbers that we have. Let's double everything. By the way, when we multiply 3 over 2 by 2, the denominator will cancel and we're going to get 3. So this is going to be 2, 3, 2, and 2. So now let's rebalance everything. We now have 4 hydrogens on the left. 2 times 2 is 4. We have 2 sulfur atoms, and 3 times 2 is 6, so 6 oxygen atoms. Now, in terms of the number of hydrogen atoms we have, it's now 4. 2 times 2 is 4. We have 2 sulfur atoms. And for the number of oxygen atoms, we have 4 plus 2, which is 6. So as we can see, these numbers are equal to those numbers. So everything is balanced at this point. So now we could focus on answering the question: how many moles of oxygen gas is required to completely react with 5.3 moles of hydrosulfuric acid? So what we need to do is start with what we're given, 5.3 moles of H2S, and simply convert it to the moles of O2. Now, we need to use the molar ratio in the balanced chemical equation. And we can see it here. It's based on the coefficients 2 and 3. So what this tells us is that for every 2 moles of H2S that reacts, 3 moles of O2 reacts with it. Now, because we have the moles of H2S on the top left, we need to put it on the bottom right of the next fraction. We want these 2 units to cancel. So therefore, the moles of O2 has to go on top. And then just put the number associated with it. There's a 3 in front of O2 and a 2 in front of H2S. So the answer is going to be 5.3 times 3 divided by 2. You need to multiply the numbers on top, divide the ones on the bottom. And so you should get 7.95 moles of O2. So answer choice E is the right answer. That's how many moles of O2 is going to react with that many moles of H2S. Now, for those of you who truly value this video, if you want to show your appreciation, one of the best ways you can do so is by subscribing to this channel. And it really doesn't take too long. Just click on that red button at the bottom of the screen, and that's it. By the way, if you decide to do so, don't forget to turn on or click on that notification bell. Now, for those of you who want to support my channel, here's the link to my Patreon page. Also, when you get a chance, check out the links in the description section below this video, because I'm going to post some other resources that you might find helpful. So let's get back to the video. 23. According to the reaction shown below, how many liters of N2O5 is required to make 3.8 liters of O2? So in the last problem, we did a mole-to-mole conversion. When dealing with gases, you can do something similar, a liter-to-liter conversion. So let's start with what we're given, 3.8 liters of O2. Our goal is to convert that to the liters of N2O5. Now the chemical equation is already balanced, so we don't need to worry about that. So let's use the coefficients. Now, we're trying to go from O2 to N2O5. So the coefficients are 2 to 1. So what this tells us is that for every 1 liter of O2 that's produced in a reaction, 2 liters of N2O5 must be consumed. When dealing with gases, the volume in liters is proportional to the moles. And so that's why we can do a liter-to-liter conversion for gases only. Now we need to set it up in such a way that the unit liters of O2 will cancel. And so it's going to be 3.8 times 2, which is 7.6 liters of N2O5. So this is the answer.